All right, 5.3, we're going to look at what's called enthalpy, and we looked at this when we saw bond enthalpy back a few chapters ago. So here's another introduction to things dealing with enthalpy and a little more in depth into exactly what that is. So we're going to start off with heat flow. Chemical reactions can result in the loss of or absorption of heat or work, but heat flow is the easiest to actually measure. So when we talk about this flow of heat, we're actually going to measure how much heat is moving. Okay, when we talk about pressure volume work, okay, in a reaction between zinc and hydrochloric acid, the only kind of work produced is the mechanical work associated with a change in volume for a system. Remember, in order to do work, you have to move something a certain distance against a force. Okay, so here we're talking about moving something. Okay, well if you've got a reaction between zinc and hydrochloric acid, like we do here with these pictures on the right. Okay, we've got zinc and hydrochloric acid. You then release the zinc into the hydrochloric acid and we make hydrogen gas. Now as you make hydrogen gas, notice how this piston right here has moved higher. Okay, so my volume has changed. So what happens is the right side piston goes up because the hydrogen gas is being produced. Now that means then that the gas or my system, that reaction, is doing work on my surroundings, which is the outside of that piston there, and it lifts it against gravity. Okay, work that is involved with the expansion or compression of a gas is called pressure volume work. And when we look at pressure volume work, there's an equation that goes along with it, and it is W, which is work, okay, equals, and it is negative P delta V. And I know it looks like a D, but it really should be one of those triangles. Just my software isn't very good for that. So negative P delta V. So work is the negative of the pressure times my change in volume. And how that works out, or when my volume expands, which is positive, okay, that means then that my work is negative, because this number here is a positive, so my overall answer then for work is a negative, which means then that energy is leaving the system as work. Okay, work is done by the system on the surroundings. Okay, a little closer in depth now, enthalpy. A thermodynamic function called enthalpy accounts for the heat flow occurring at a constant pressure where there's no forms of work other than pressure volume work. So enthalpy, which is in H, is my internal energy plus the product of my pressure volume. So H equals E plus PV. Okay, enthalpy is a state function, which means I don't care how I get there, just where I start and where I finish. Okay, because internal energy, pressure, and volume are all state functions. Okay, when a change occurs at constant pressure, that means then that delta H equals delta E plus PV. Okay, remember deltas are final minus initial, so we're substituting in there final minus initial. Then what we're going to do is a little bit of equation work here. Okay, you recall the following ideas. W is negative PV, and delta E is heat plus work. So what we do is we substitute that negative W for P delta V. We substitute in Q plus W for delta E, and we get enthalpy is heat plus work, parentheses, minus work. Well, the works cancel, and enthalpy really equates to heat. So what this is saying is that the change in enthalpy equals the heat lost or gained if I'm at a constant pressure. So you're doing all of this work pretty much, driving these equations to get at the idea that enthalpy, if I have constant pressure, is the exact same thing as my heat that is lost or gained. So what's very good now is that since delta H equals my delta E, because P delta V is small, so P delta V part is very small, okay, so I don't care about that. Enthalpy is more useful than internal energy because most reactions occur at constant pressure, and Q, my heat, is really easy to measure or really easy to calculate. So what we end up with then is a really easy way to figure out endo and exo, and this, again, this big long thing we're getting at, that heat pretty much equates to my energy. Okay, so if my delta H, my enthalpy, is positive, that means that my system gained heat, which means then that we are endothermic. Okay, heat went in. If you have a negative delta H, that means that my system lost heat, which means as we're losing something here, we're looking at an exothermic reaction. So since heat and enthalpy are really one and the same for what we deal with, it's really easy to see then that we have an endothermic or an exothermic reaction just by my enthalpy, which are numbers we're going to look at here throughout the chapter. So since delta H is a state function, delta H only depends on the initial and final states of the system and not how we got there. So all I care about is what's the end result. Where are we at? Okay, and these little boxes here to the right explain what I just said. Okay, some practice. Indicate the sign of the enthalpy change in each of the following processes that are carried under atmospheric pressure. So that means I have constant pressure, so we can get rid of all that P delta V stuff that I really don't care about. And we're going to decide whether it's endothermic or exothermic. So in essence, remember, since I don't care about the work, since really work stays the same, delta H equals my enthalpy, which pretty much equals Q. So if an ice cube melts, in order to melt this ice cube, I have to absorb heat. Since I have to absorb heat, that means that my Q is positive, which means that my delta H is positive, which means that I am endothermic. Okay, a little bit different example. I have 1 gram of butane that's combusted in sufficient oxygen to give complete combustion of CO2 and H2O. So here we're in a combustion reaction, and combustion reactions give off heat. Okay, they get very hot, and you're going to blow something up, it gets very warm. So we're going to lose heat. Since I'm losing heat, that means my Q is negative, which means my delta H is negative, which means that I am exothermic.